Hello, class. This is Mr. Hart, and this podcast we want to start the end of year topic on quantum mechanics. Okay, so if you're watching this video, you're probably pretty brave for wanting to understand quantum mechanics. Before we get started in this, let me say that I want to make it clear that this is only going to be conceptual. We're not going to be able to dive into the mathematics, and also understand this is just my best understanding and ability to try and explain the world of quantum mechanics. Okay. It's very strange and it's hard to explain clearly, so I apologize if anything's unclear or inaccurate. Okay, even certain scientists that have studied quantum mechanics for years have troubles trying to explain what's going on, and things are constantly changing in the world of quantum mechanics anyways. So just understand that not everything I say may be necessarily true a couple years down the road, and I may not be explaining it the best I can be, but I will do my best to kind of give you a foundation in the realm of quantum mechanics. Okay. So let's start with quantum mechanics. It's kind of this world of probability. It's looking at the things that are very small, atoms, electrons, leptons, all these, super small particles, and things don't behave the way we would expect them to. Okay, in the classical world, or the world we live in, kind of the big world, okay, things behave very predictable, in a very predictable fashion. When we started analyzing quantum mechanics and realized things happen based on probabilities, it kind of just blew people away, and most scientists actually didn't believe it for a long time. They thought it was just poor data and things like that. There's actually a funny story that's told to be about Einstein. I don't know if it's true or not, but one of his grad students noticed that every year Einstein gave the same test for one of his classes, and his grad assistant said, Dr. Einstein, why are you giving the same test every single year? And Einstein says, well, that's because the answers have changed since last year. And that's kind of the way quantum mechanics is. We're constantly finding new things because things just don't behave the way we would think. Everything's based on probability and stuff like that. You hopefully watched the video about the double slit experiment. It's a great video that kind of explains kind of the foundation of where quantum mechanics came from and when we started really analyzing these things. But in that video, it kind of explains that they were shooting electrons through this barrier, and it had two slits in it, and if there were particles, they were expected to have just two bands on the other side, but instead they started behaving like waves. They started having a wave interference pattern, which is odd because electrons are not supposed to be waves. Okay, but because of this double slit experiment, we started realizing that quantum mechanics has this weird property where everything's based on probability, based on waves. And because of this, we come up with the idea of what is known as wave-particle duality. Okay, trying to describe this well is hard. Some scientists just like to say, well, you treat it like a wave when it's convenient, and you treat it like a particle when it's convenient. Okay, that's kind of one way to think about it. But I like to think of it this way. It's kind of a simplification, but basically any quantum object will behave as a wave of probabilities until it's observed at a certain location. Okay, so those electrons on the double slit experiment behave like waves until they hit that barrier right here, and they're observed basically by the barrier. Okay, they're detected. Once they're detected, they are behaving like a particle, but until then, they behave like a wave. Okay. Another way to say that is when unobserved, electrons behave like waves, and when observed, electrons behave like particles. Okay, and not just electrons, but any one of the very small particles in the quantum world. Okay, these wave of probabilities have been described well mathematically, and we call it the quantum wave function. Okay, and this is kind of one of the very difficult things to describe mathematically in quantum mechanics. The person that was able to describe them mathematically is a man by the name of Erwin Schrodinger. Okay, you probably heard his name because of Schrodinger's cat. It's kind of a terrible analogy in my opinion, but that's the most famous one. But Erwin Schrodinger gave this analogy that electrons behave like this cat that's in this box. Okay, and you have that box. Okay, let me see if I can draw it at all. He imagined that you have a box, okay, and you have a cat. Okay, I can't draw a cat. There you go. There's a cat. And in that box, you have some poisonous food with the cat. Okay? And his explanation was, and this is kind of a terrible explanation, is that basically if you're not looking inside the box, the cat is in a superposition of two states. It's both dead and alive, because up until that point, you don't know if it's eating the food or not, or if it's still alive, okay? And so it's kind of just in between two of those states. It will be in both in your mind, basically, until you actually open the box. And so once you open the box and look inside, okay, then you'll see if the cat is actually dead or if the cat is actually alive, okay? You observe it. Now, it's not my favorite analogy, and Schrodinger was actually talking a little bit more about the spins of electrons and this type of stuff, but we won't get into that quite yet. We'll look at that next time. But the point is, basically, things behave like probabilities until they're observed, okay? And he described this quantum wave function, okay, that says, basically, we have a wave, and however that wave behaves describes the probability of finding a particle at that location, okay? So, for example, if this is our quantum wave function, our most probable location of finding that electron or whatever it is at this position. Now, when we get it on the detector, it probably won't be at that position. It may be around that area, but that's the most probable position, okay? Most of the time, it will land between this area, right, the high part of the wave right here, okay? But sometimes it will be over here, sometimes it will be over here. But until then, it's in all those locations until we detect it, okay? That is the quantum wave function, and that's what explains the weird pattern we see in the double slit experiment, okay? Until those electrons get detected and observed, the wave is interfering with this double slit. And when that happens, we get a wave interference pattern. So here's another visualization. The wave interference pattern looks like this. Okay, if you send a wave through, its interference pattern will look like that. So this is the quantum wave function that we see for the double slit experiment. So what does that mean? Okay, well, if we have electrons hitting that wall, okay, let me do a different color. The electrons most likely are going to hit in the middle of the wall, right? However, electrons also can likely hit on this side and on this side, and there's going to be a couple on that side, right? And this is the band we see, okay? And so that interference pattern is the wave, okay, on the wall, okay? But we only detect at one location. So if we just keep sending electrons through and sending them through and sending them through, eventually this pattern emerges. It's the interference pattern of the wave. But at one single time, we only detect the electron at one location, okay? Now, there's other probabilities that can hit, maybe there and there, but you'll notice they're very, very small, but that doesn't mean that they don't exist, okay? So that's why it's so weird. And basically, the amount of electrons you should be detecting in a certain location is basically the wave probability that they'll be detected at that location, okay? So it gets emitted, the electron behaves like a wave, it interferes with the two slits, creates this interference pattern, and then it gets detected at one of those locations each time, okay? And that's the quantum world. That's the crazy thing. And that's what's led to so much strange and weird phenomenon is this double slit experiment, okay? It's kind of the foundation of quantum mechanics. And so quantum wave functions are very cool. This idea that something behaves like a wave and has this whole probability and just gets detected in one point leads to some really cool stuff. And that's what we're going to look at in the next lesson. But for now, make sure you do this homework, okay, the quantum wave function, okay, and then make sure you watch the next lesson because there's some cool stuff we're going to get to. But hopefully that makes sense. Let me know if you have any questions, and thank you for watching.